so we stopped here, and what we were looking at is the relationship between the function and its derivative. And what we notice is that when the function, the derivative of the function drops a power. So when our function was a cubic, our derivative was a quadratic. When our function was a quadratic, our derivative was linear. So our derivative clearly is dropping down a power when we're looking at these polynomial functions. Okay, so past problems we were finding the derivative function by inspecting it graphically, by drawing tangent lines and finding the slope of the tangent lines. Now what we want to do is find the derivative of a function that's defined numerically, or in other words, on a table. What we need to remember again is that the derivative is the slope of the tangent line. And we're going to use this idea of slopes to find the derivative. So what we've got the unemployment rate varying with time. So here's time, and here's our unemployment rate. Sorry about the outdated information. This is a pretty critical topic as we go into this election upcoming, the idea of unemployment and what the candidates are going to do with that. So a relevant thing to be looking at. But what we want to be looking at is change in unemployment rate. So each one of these, that's the unemployment rate for each year. We want to know year after year, how is the unemployment changing? So we want to evaluate the derivative of the unemployment rate, and the derivative is the instantaneous rate of change. Okay, so we want to do that from 86 to 94. All right, so what we want then is the time and derivative, and we want a table of that. So we've got 86, 87, 88, 89, 90, and I'm not going to do all of these because you're going to see pretty quickly that it gets pretty tedious. So, and in your work tomorrow in class, we're gonna hammer out some of this tedious work, because I do think that it's important for you to really recognize that that derivative is just the slope. So if we're looking at 1986 to start off with, and we want to find what's the derivative in 1986, what we know is that from 1986 to 1987, our unemployment rate went down by 0.8. So in 1 year, my unemployment rate went down negative 0.8 in that 1 year. So this is my change in unemployment as a function of time. And even though this isn't the instantaneous rate of change, it's the best we can do with this table. So all we're going to look at is the year and the closest year to it. So in this case, we have 1986. We're looking at the next year closest, 1987. And from 86 to 87, we get a change of negative 0.8. Now, what about if I wanted to find the derivative there? Well, here I've got a point on either side. I've got 1986 and 1988. So I'm guessing that your intuition is probably right, and that you're thinking we're going to get two slopes, and we're going to average them. So the u, or the change in u with respect to time between from 86 to 87. Well, we already calculated that right up here. We know that that equals negative 0.8. But if I'm looking at from 87 to 88, the change in u with respect to time, well, I was at 5.5 in 88, subtract 6.2 in 87. That's the change in unemployment in that 1 year. And that equals negative 0.7. So if we're thinking about the rate of change of the unemployment in the year 1987, well, the year before it, from 86 to 87, we had a change of negative 0.8. From 87 to 88, a change of negative 0.7. So the instantaneous rate of change in 1987, we're going to approximate as the average, negative 0.8 plus negative 0.7 divided by 2, finding the average, which equals negative 0.75. Let's do two more of those. So let's look at 1990. So in 1990, we're going to look at the change from 89 to 90 and the change from 90 to 91. So looking at 89 to 90, we've got 5.6 minus 5.3 in 1 year. That was the change in unemployment. So here, 0.3, a positive change in unemployment. In this case, positive is a bad thing because we don't want unemployment to increase, but in 1990, from 89 to 1990, it did. Now looking from 90 to 91, so now we're looking at these points. So from 90 to 91, we had a change of 1.2 in that 1 year. So that was a real bad year as far as unemployment goes. And then to think about, well, what's that average rate of change? What's the average between 89 to 90 and 90 to 91? Well, let's take the average. So we're going to approximate the instantaneous rate of change in 1990 as the average of 0.3 plus 1.2 divided by 2, which equals 0.75. And so that would be our approximation for the average rate of change in 1990. Well, doing one more, let me just remark. For any year that's not an endpoint year, so anything that's in between 86 and 94, but not 86 and 94, you're going to get 2 points on either side and take the average. But for the endpoint year, if I was trying to find the instantaneous rate of change for 94, I can only choose 1 point. I can only choose this information there. So, the instantaneous rate of change in 94 is the rate of change between those only 2 points, because there's only 2 points I can choose. So 6.1 minus 6.9 over 1, which is negative 0.8. Now we could go forth and fill in the other years, but we're just finding slopes, and that's something you've done in Algebra 1, slopes and averages. So for now, I think the technique is very clear, so we can just skip ahead where we can see an actual table already computed of time and the respective derivative. So here we have a chart, and going backwards, each of we got some of these values right, so we should feel good about that. In 86, it was negative 0.8. 86, negative 0.8. In 87, it was negative 7.5. And just trust me that we did the other ones right, and these are all correctly formulated. So up here, we've got, what we did is we plotted unemployment as a function of time, and then that's up here. And then in the second graph, we looked at the derivative. So we're looking at the rate of change of unemployment as time goes on. And I think some of the things that are important to look at, it's important to notice, is that, well, let's see. So first off, I'm looking at my unemployment. When my unemployment is going down, is decreasing, I should have a negative rate of change of unemployment. So when my unemployment is decreasing, notice that my unemployment are all negative values. So these are all negative values when my unemployment is decreasing. And when my unemployment is increasing, when my unemployment is increasing in red, that these all have positive slopes. So it makes sense that my derivative is positive. So the rate of change is positive, or the slopes of the tangent line is positive when my function is increasing. And when I go back to decreasing again, my slopes go back to being negative. And then the other critical thing is that when I reach a local minimum, my derivative is 0. In other words, I have no rate of change there. It's not changing instantaneously. There's no instantaneous rate of change, or in other words, the unemployment is staying at a constant level. It was decreasing, 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 and then it reaches this blue and it stops for a second, and then afterwards it starts increasing again. And so we notice that there my derivative is 0. And likewise, when I have when I've got a max value, my tangent line is 0, which we see is 0 in terms of my slope. This is a hard jump to make, but we're really going to start needing to understand that when we see a picture of the derivative, the function itself, we can understand what the derivative looks like by thinking of whether or not the function is decreasing, increasing, or whether it has a minimum or a maximum, and what that corresponds to on the respective derivative graph. Okay, so this is what we're going to be doing the next day. So we're done for today. Looking back at what today we've done. So first thing, or the last thing that we did rather, is we took a chart and we looked at the slopes to get a chart of the derivative function. And then we were able to plot the function itself along with its derivative function. And we're looking at relationships between the derivative and its function. Going backwards, the other thing that we were doing today is that we're looking at a function and graphically looking at a function and drawing tangent lines on this function like we did, so that we could then estimate a table of x and its derivative function, so that we could then plot the derivative function. And we also recognized the relationship between a function and its derivative in terms of the powers. When we take the derivative, the power drops. These are all big ideas. Okay, that's it for now.